Welcome back. So we are continuing on with cardiology, and we're going to start talking about blood flow and pressure. So we're going to start talking now about blood pressure and flow. And before we talk about blood pressure from a kidney standpoint and all of that, we're going to just talk about basic physiology on what happens in the vessels. So when we talk about vessels, we need to talk about pressure inside of a vessel. So how that is determined by is basically resistance and change of pressure. So if you see there, you'll see that resistance, if you want to think about it this way, is the size of the vessel or the diameter. So a small diameter, high resistance. Large diameter, little resistance, okay? The other thing is that when we're talking about pressure, it always flows from high pressure to low pressure. The arterial system is a high pressure system. The venous system is a low pressure system. Also, the pulmonary arteries are also, and veins are also a low pressure system, okay? So the other thing that we think about is the protein and the pressure coming from the heart. Now, the protein is oncotic forces. The pressure from the heart is hydrostatic forces. And we can learn about this through the Starling equation. I know, we're going to do an equation. So let's go ahead and work this out on a whiteboard together. So basically we need to review what the fluid exchange is across the capillary walls. We have 4 different pressures. We have oncotic pressure in the capillary, and then oncotic pressure outside of the capillary wall. We have hydrostatic pressure in the capillary and hydrostatic pressure outside the capillary wall. So let's take a peek at the equation, all right? So when we look at this equation, we have fluid movement. That is what we're trying to solve for. Is it positive or negative? And then we have this hydraulic conductance. We're going to leave that out for now, all right? So basically now we're left with capillary pressure inside and outside and hydrostatic pressure inside and outside. And just to review what hydrostatic pressure is, that is pressure coming from the heart, okay? Oncotic pressure has to do with albumin and pulling fluid out or in according to where the most protein is, all right? But let's take a look at this. So let's solve a problem. Let's say that PC, or capillary hydrostatic pressure, is 30. Now, let's say that interstitial hydrostatic pressure, which is PI, is 5, all right? So put that in parentheses, that's going to equal 25. Now, let's take that minus capillary oncotic pressure, which we're going to say is 6,000, just because, all right? 6,000, minus the interstitial oncotic pressure, and we're going to make that 5,975, okay? Subtract that first, and now you have 25 minus 25, which is 0, all right? So what does that mean? Well, 0 would mean there is no fluid movement. All right, let's change our numbers a little bit. Let's make it 40 minus 5, okay? 40 minus 5 and leave the rest of the numbers the same. Now we have 35 minus 25, which gives us a positive 10. Well, what does that mean? Well, if you have a positive JV, a positive fluid movement, that means that you have fluid going from the vessel to the tissue. All right? A negative JV would mean that we are sending fluid from the tissue to the vessel. I'm not sure if you'll actually have to solve an equation anytime soon, but it's really important to know the difference between oncotic pressure as well as hydrostatic pressure. Now, continuing on with just pressure and what controls it, we're going to talk about neuroregulation of blood flow. Now, when we think about neuroregulation of blood flow, we're talking about our baroreceptors, and those are going to be found in the aortic arch and carotid sinus, and those are going to change things via our sympathetic nervous system. So what happens is it sends a signal via the vagus nerve and the glosopharyngeal nerve to the medulla, which we've already talked about, right? Because that also is the rhythmicity center for our breathing. Well, this also then is going to control our peripheral resistance, so if our vessels need to contract or dilate, as well as it's going to increase or decrease cardiac output. And we're going to talk more about cardiac output in a minute. But when we talk about things like blood pressure and volume, we also have hormonal involvement, and I've listed them there. I'm not going to get into them now because we're going to talk a ton about ADH and angiotensin II and aldosterone in a minute, but this is good review here. So the other thing then, when we talk about cardiac output, and we're going to skip kind of over ejection fraction for a second, is cardiac output is basically how much our heart is pumping out by how much time, okay? And there's an equation there. Cardiac output equals stroke volume times heart rate, all right? So if you think about heart rate, we know what that is, right? But what is stroke volume? Well, let's take it back a page and look at that. So there's something called ejection fraction, and ejection fraction is basically how much your heart is pumping out per unit of time. Now, when we think about this, we want one that's over 50%. Anything less than 50% is what we considered a damaged heart, or somebody would have congestive heart failure. Greater than 50%, like 55%, that's in a healthy adult individual. All right, so when we think about ejection fraction, we look at something called end diastolic volume, which basically end diastolic volume is exactly what it sounds. During diastole or relaxation, end diastolic volume is how much blood a ventricle can fit in it, all right? And then it contracts that out, all right? After it contracts it out, that is called the end systolic volume. Totally makes sense, right? Well, the difference between those two is our stroke volume, all right? You want a high stroke volume. That makes sense. So when we then look at cardiac output and we take how much blood we're pumping out over a period of time, that clues us into how healthy our heart is. And there's different things that control that. And if you look there, I've listed some of them. So things that affect stroke volume are different things like medications. So we know that digitalis, for example, digitalis increases sodium. So that is going to help our contractility versus things like beta blockers and calcium channel blockers. Those are going to decrease contractility. All right. There's other things too. If you have a high pressure system, like let's say somebody has a pulmonary arterial disease. Well, that pressure that they're pumping into is so hard, it's going to decrease our contractility. So different things like that definitely play a part. All right. So a couple other things is when we talk about just our regulation of blood flow, we also have to think about how massively our kidneys play into that as well. Now, our sympathetic system has a lot to do with this, because if you are in fight or flight, is your body going to think, oh, I have to go to the bathroom? No, it's not, right? Your heart is going. We just talked about sympathetic system controlling our medulla oblongata, but it's also going to have constriction of our arterioles as well. So if you constrict the afferent arteriole that goes to the glomerulus, and again, we'll talk about that when we're talking about our nephron, it's going to decrease glomerular filtration rate, increasing blood volume. All right? Instead of peeing out things, you're just going to hold on to it during that fight or flight situation. The other thing that we need to talk about is our hormonal control. And I have a chart of the aldosterone pathway that I'm going to put up here, and we're going to talk about it on a whiteboard. So if you look at this pathway, this is the angiotensin II pathway. And this is a great way to visualize how blood pressure and the kidneys are related. So if you look at that top part, it says blood pressure and blood to the kidneys decreases. Well, when that happens, those JG cells are stimulated. What do JG cells release? Right, renin. So they release renin, and renin's job is to change angiotensinogen to angiotensin 1. Well, what changes angiotensin 1 to angiotensin 2? Right, ACE. And actually, this is where our ACE inhibitors work. So we can go ahead and write it right in. All right, ACE. So ACE changes angiotensin 1 to angiotensin 2. And look at what angiotensin 2 does. Angiotensin can either go and just cause vasoconstriction of the arterioles, and it is a potent vasoconstrictor. When you have a vasoconstriction of the artery, what happens? Right, you have an increase in blood pressure. Now let's go the other way. If angiotensin 2 goes to the adrenal cortex, what does it release? Right, aldosterone. And aldosterone's whole goal is to take water and salt out of the nephron on the kidney and put it back into the blood. So when this happens, your blood volume increases, again, increasing blood pressure and blood volume. So obviously, the more blood volume you have, the higher the blood pressure. We just saw that. Another hormone that we need to talk about too is ADH, and there's also a chart in your book that covers that. But basically, if you are dehydrated or you have increased salt intake, you have a high blood osmolality, and that's going to stimulate those osmoreceptors in your hypothalamus, and it's going to do two things. It's going to make you super thirsty. You're going to drink more water, which is going to increase your blood volume, or it's going to send a note to your posterior pituitary saying, hey, I need more fluid, and it's going to release ADH, which is going to go to your nephron and put fluid or water back into your bloodstream. When that happens, then that also increases blood pressure. So I would be aware of all of those. They're all really important in blood pressure regulation. We're going to take time out here. We're going to answer a few questions. And when we get back, we're going to talk about the urinary system.